Good afternoon, everybody. It's my pleasure to introduce Guillaume Barraquand, who is a CNRS researcher at École Normale Supérieure de Paris in the physics lab, in fact. And he will talk about invariant measures for the Kpz equation. So thanks, Guillaume.
Hello, everyone. Thank you, Marielle, for the invitation. So as you said, I hope that you can hear me. In principle, it's okay. So as you said, I will talk about the Kpz equation and focus on the question of finding invariant measures. So the Kpz equation describes, so this is an emblematic model to describe interface growth. We'll restrict to one special dimension. And so in that case, the Kpz equation describes the evolution of a function h of a space variable x, which evolves in time according to the equation that is written on the slide. So the time derivative of the function h equals the Laplacian plus the square of the gradient plus some noise term that I denote by xi. And it's not totally clear as it's written what it means by this equation, but if xi is a white noise, in particular white in time, then the time evolution of the function h will be a Markov process. And then one can ask what are there invariant measures? If yes, are they unique? Can one classify them? More than existence and uniqueness, can one describe them precisely as some well-known processes like Brownian motion or something else? But the answer depends on what space we are considering this equation. So the space I've denoted by capital X here, and there are a few natural cases to consider. Maybe the first one is to consider the real line where X equals R. In this case, the invariant measures have been known for a very long time. One can also consider periodic boundary conditions. So consider a cycle, X equal R quotiented by Z. But one can also consider more complicated boundary condition and consider Kpz growth on an interval. So for instance, the interval 0L, where L may vary. And one can also consider a situation with only one boundary condition. So consider Kpz growth in a half space or plus. So that's the. Actually, I will tell you some invariant measures for at least for all of these cases. However, in general, uniqueness is not known. So before telling you exactly what I'm going to do in this talk, let's address the simplest cases. And the simplest cases are the case where we consider unbounded growth. So we have no boundary condition or periodic boundary condition. So let's first assume that X equal R. So we are considering the Kpz equation on the whole line. And so far, I haven't tell you exactly how the Kpz equation is defined, but I will just state the result, and then I will tell you more precisely how everything is defined. So the first thing is that there is no invariant measure in the strict sense. This is because typically the height htx, it behaves like a constant time t. So it cannot be stationary in t. It diverges. However, so what I've written in the slide is a little bit pedantic. I'm saying that there are no invariant measure if we consider the evolution of these functions of space. But if we consider these functions of space modulo constants, then there will be invariant measures. So modulo constant, then the profile will be invariant, or said otherwise, the process of spatial increments may be invariant. So very concretely, this means that for the Kpz equation on the whole line, or if at time 0 we start from h0x being a Brownian motion, so I denoted by bx superscript mu, a Brownian motion with drift mu, then it can be shown that for all time t, the difference between the value of h at x and at 0 will again be a Brownian motion. So htx minus ht0 will again be distributed as a spatial process in x as a Brownian motion with the same drift. So So this is why we say that this is in that sense that we say that the Brownian motion is invariant for the Kpz equation on the whole line. So this has been known for a very long time. At least for physicists, this is known, in my opinion, at least since the work of Forster, Nelson, Stephan from 1977. So you may notice that this work from 1977 is actually appeared before the work of Kardar-Parisi-Zhang in '86, which is supposed to have defined the Kpz equation. But Forster, Nelson, Stephan discussed the case of the Burger's equation, which is very related. So this was in physics, and then this stationary result, it has been shown completely rigorously by Bertini and Giacomin in 1997. And I will explain actually what goes into their proof. And there are other approaches more in the spirit of stochastic PDEs, more recently by Funaki and Quastel. So here I insist that what is stationary is the increments in space. So htx minus ht0 is distributed as a Brownian motion. However, the random variable ht0 has a very complicated distribution, and it's very correlated to the increment process. In certain cases, one can say something about this variable ht0 for certain initial condition. One can show that it behaves as a constant time t plus some non-trivial fluctuations, which typically arise on the t to the 1/3 scale. But I will not talk about this at all in this talk. So this is related to integrable probability, random matrix theory, but I will not talk about this at all in this talk. We will really focus on invariant measures. There is another case where the answer is relatively simple. This is the case of periodic boundary condition. So if we consider the Kpz equation on a cycle, then this is the Brownian bridge, which is the unique invariant measure. The fact that this is an invariant measure can be shown in the same spirit as Bertini and Giacomin. But then what is special is the fact that it has been proved that this is the unique stationary measure by Heirer and Mattingly in 2016. And I think this is the only case where one can show that the invariant measure is unique. So this is for the simple case. Now, what I want to address in this talk is what happens when we have some boundary condition. And what will happen is that the invariant processes, except in some very special cases, will not be Brownian anymore. The increment process will not be translation invariant anymore. Actually, these processes will not be Gaussian anymore, although they will be built using some Gaussian variables. But they can be characterized very precisely, and these are interesting processes. So first, I will explain what Bertini and Giacomin did, how to find invariant measure on R and prove that these are stationary. Then I will state results for Kpz growth on the segment, then for Kpz growth on R plus, a half line. The arguments in both cases are actually different, although these two cases are related. And in the end, I will give not a full proof, but I will describe some of the ideas that goes into the proof of the two cases, the segment and the half line. So before going into the results, etc., let's pause a minute and ask the question how to find invariant measure of nonlinear stochastic PDEs. So here the question is still a bit vague because I haven't described very precisely what it means for a function to be a solution to the Kpz equation, but this is a problem in general for nonlinear stochastic PDE. There is, to my knowledge, no general method to find invariant measures. And so if we see these as stochastic processes on the space of, say, continuous functions, it's difficult to describe precisely what is the generator or the semigroup associated to this Markov process. And so I wouldn't know exactly how to start working on trying to prove that a certain distribution on functions is stationary. However, a method that works is to consider approximations of these stochastic PDEs. discrete approximations that are given by exactly solvable models for which one can find invariant measures and characterize them very precisely. So this is the approach that I will describe in this talk. And there are two very large classes of discrete models that converge to the Kpz equation. One class are interacting particle systems, such that ASAP, the asymmetric simple exclusion process. Another class are directed polymers. And in that case, the exactly solvable one that we'll use is called the log gamma directed polymer model. It was introduced by Sepalainen. Actually, it was introduced precisely because its stationary measure can be computed. But this is a variant that we will need. We will need a variant of that model with boundaries. So now I want to explain what Bertini and Giacomi did, how they found invariant measure for the Kpz equation on a whole line. So as I said, this goes through ASAP. So the asymmetric simple exclusion process, this is a continuous time Markov process. We have particles on integer sites, at most one particle per site, and they may jump to their right or left neighbor, provided the target site is empty, at rates, rate 1 to jump to the right, and rate q to jump to the left, where q is some asymmetry parameter. Many things are known about this process, in particular the fact that for any rho, the measure which puts a particle on each site with probability rho independently on every site is invariant. So the product Bernoulli measure is invariant for these dynamics. Then, in order to connect to the Kpz equation, there are many ways to describe the state of the system. For instance, one can say for each site whether it's occupied or not. But to connect to the Kpz equation, it's better to define a height function. So we define a height function htx, capital htx, so that its gradient, so htx minus htx minus 1, will be 1 plus 1 or minus 1, depending on whether the site x is occupied or not. So strictly speaking, this defines the function capital H up to a constant. And if one really wants to define it precisely, one can fix that ht0 is the number of particles which have crossed the origin. Although, since we will discuss invariant measures up to a constant, so actually we don't even need to define, it's totally fine to define the height function just up to a constant. So this is ASAP. And how ASAP is related to the Kpz equation. So that was the main result of Bertini and Giacomini in 1997. But before stating it, I want to explain you what does it mean to solve the Kpz equation. So on the top of the slide, I recalled what is the Kpz equation. So here, x is in R, and xi is a space-time white noise. And the way a solution is defined is through the multiplicative noise stochastic heat equation. So dt z equals 1/2 the Laplacian plus z times the space-time white noise. We will, so if we put h equal log of z, then ignoring all issues of regularity, etc., the Kpz equation gets transformed into the multiplicative stochastic heat equation. And it turns out that this stochastic heat equation can be defined through stochastic calculus. So as usual, for an equation of the form time derivative equal Laplacian plus something, so it's an equation of the form heat equation plus potential will be defined using the heat kernel as it's written. So I don't think that you see, do you see my mouse or you don't see my mouse?
We see it.
Yeah, we see it, sorry.
Oh, great.
Yeah.
So the solution to the stochastic heat equation is defined like this. So this is as would be any equation of the form heat equation plus potential. So ZTX must be the convolution between the heat kernel and the initial condition. plus an integral in time and space of the heat kernel against what I call the potential, which here is the z times psi. And in this case, for space-time white noise, this integral is a stochastic Ito integral, but it makes perfect sense. So we can solve z, and then we will say that h defined as the log of z will be a solution to the Kpz equation with initial data log of z0. And this is well defined. One can show that z is positive. So that's how the Kpz equation is defined. And the relation to ASAP is that if you recall that capital H was the height function of ASAP, and Q was the asymmetry parameter, you take Q to the height function, essentially, you call that Metcalfe Z. And okay, one has to scale a certain number of parameters appropriately. We take Q, the asymmetry parameters, as exponential of minus epsilon. Epsilon will go to 0. We scale the time as epsilon to the -4, space as epsilon to the -2. And then this Metcalfe Z will converge to ZTX, a solution to the stochastic heat equation. And so if you take the log of both sides of this, you get on one side the height function of ASAP, and on the other side the Kpz equation. So this means that ASAP height function converges to a solution to the Kpz equation, and that was the main result of the paper of Bertini and Giacomin in 1997. In that same paper, as a corollary, they explained that since we know that the product measure Bernoulli rho is invariant for ASAP, and that under that measure, the height function of ASAP converges to a Brownian motion with drift that depends on how rho is scaled, then it implies immediately that the Brownian motion with any drift is invariant for the Kpz equation. So now we will try to explain how to adapt this argument in cases where we have boundaries. So I will first discuss the case of the Kpz equation on the segment. So we fix a segment 0L, and we look at the same equation on a segment. So here, for the solution to be unique, as usual with PDEs, we need to impose boundary conditions. So since I told you earlier that typically the Kpz equation, it behaves at large time as a constant time t. So it would not make a lot of sense to fix the value of h at 0 and L. However, what does make sense is to fix the derivative of h. And this makes sense physically because if you, through the relation between ASAP and Kpz equation, the derivative of h is related to the gradient of capital H, ASAP height function, which is essentially the density in ASAP. So fixing derivative corresponds to fixing density in discrete models, which makes sense physically. So we will impose some Newman type boundary condition. dxh at x equals 0 will be some parameter a, and at x equals L will be some parameter b. That said, so this makes sense physically, but it doesn't make sense mathematically because htx is not differentiable. So we'll need to explain a little bit more precisely what do we mean by these boundary conditions. And this is how we do it. So as for the Kpz equation on the whole line, we go through the stochastic heat equation, and the boundary conditions that I've described in terms of the stochastic heat equation, they become the fact that dxz at x equals 0 must be a times the value at x equals 0, and dxz at x equals L must be b times the value at x equals L. And then we will define a solution a little bit through the same method as for the whole line, except that now the heat kernel that we should consider will be the heat kernel that is the solution of the heat equation on the finite segment 0L, which satisfies the boundary conditions that we are interested in. So we said that H solves the Kpz equation on the segment 0L if H equals the log of Z, and Z solves, so ZTX equals the convolution of initial condition with the heat kernel on a segment, plus an integral in time and space of the heat kernel with against the potential Z psi. And this heat kernel, so I parameterize it using letters U and V. So instead of parameterizing boundary condition by capital A and capital B, I will parameterize them by U and V. So here you see that my capital A, it has become U minus 1/2, and my capital B has becomes minus V plus 1/2. It doesn't matter too much. It will just make some statements simpler later. So from now on, we'll not have parameters A and B, but rather U and V, and U corresponds to the left boundary and V corresponds to the right boundary. So the first result about invariant measures of the Kpz equation on a segment is from Corwin and Kpz from last year. And it says that for boundary parameter U and V such that U plus V is positive, and okay, in the case L equals 1, that last condition is purely technical. First, there exists a stationary process that I will denote by HUV. It also depends on L. And one can characterize its finite dimensional marginals, so the joint law at positions x1 to xk. And these are characterized in the paper of Corwin and Kpz by some multivariate Laplace transform. So the multivariate Laplace transform of the increments of the stationary process is given by some formula. That formula is rather complicated. I will give you a sense of how it looks like later, but it's quite complicated. And a second result is that when U plus V equals 0, then this process, this stationary process HUVL is a Brownian motion with drift U equals minus V. This second step is actually important in order to show the first step. But so here, okay, it's an existence statement. They also conjecture that this stationary process should be unique, but the characterization of the process itself is quite complicated. The formula is so complicated that I didn't want to write it on the slide. And there are several things that motivate a further understanding of these stationary processes. The first thing is that U is the left boundary parameter, V is the right boundary parameter. And so there should be some symmetry. If we exchange U and V, it should correspond to reversing space. And this should be apparent on the formula, but actually it's not so apparent on the formula. You cannot see it because I haven't written it, but I'm claiming it. Another thing is that the formula should simplify a lot when U plus V equals 0, since I say that at U plus V equals 0, we get just a Brownian motion. So at U plus V equals 0, this big formula should become just the Laplace transform of a Brownian motion, the multi-point distribution of a Brownian motion. But it's possible to get it from their formula, but it's actually not so easy to do as a calculation. And the last point is that this result is restricted to U plus V positive, but in principle, one can consider the equation with U plus V negative, and it would be interesting to find the invariant measures as well. So with these three motivations in mind, I state another result. So the Laplace transform formula of Corwin and Kpz was inverted in order to describe the stationary process purely probabilistically. So this has been first done in a paper of Brick, Kuznetsov, Wang, and Veselovsky, and then a few weeks later appeared a physics paper with Pierre Doussal, which proposed a slightly different characterization, but which eventually was proved to be equivalent to the first one by another paper of Brick and Kuznetsov, so that this is now a theorem. The statement that I show you on the slide here is the one that is taken from my paper with Pierre Doussal. So to describe this process, the stationary process HUV, I first introduce some piece of notation. For any continuous process xt, I give a notation for exponential function also. At of x will be the integral between 0 and t of the exponential of minus twice the process xs, integrated between 0 and t. And so then one can show that when U plus V is positive and L equals 1, so using the same assumptions as the statement of Corwin and Kpz, HUV is the sum of two things. The first one, W, is just a Brownian motion with diffusion coefficient 1/2, but we don't really care about that. plus another process, capital X, which is a bit more complicated. So this process X, it's a continuous process. It's independent from the first one, W. And its distribution is absolutely continuous with respect to the law of the Brownian motion. It's absolutely continuous, and the Radon-Nikodym derivative is very explicit. So the Radon-Nikodym derivative is given by a product of two exponential functionals raised to the power minus u and minus v. So the second line here is just using the definition of my exponential functional. The Radon-Nikodym derivative takes this very explicit form with two integrals of exponentials of the process raised to some powers u and v. Some remarks about this result. So first, what it means, the fact that X is absolutely continuous with respect to the Brownian and with this explicit Radon-Nikodym derivative. I just remind you that it means that if you have a functional defined on continuous processes, then the expectation of any such functional will be proportional to some renormalization constant. To compute this expectation, you just need to compute the expectation over the Brownian motion of the same functional times this Radon-Nikodym derivative, and there have been many works in the physics and mathematics literature computing this sort of exponential functional. So actually, there are many things can be computed very explicitly here. So this new description of the stationary process HUV has several advantages. One is that here, if you exchange u and v, it really corresponds to exchanging x index x and xl minus x minus xl. So really here, it can be seen on the Radon-Nikodym derivative that exchanging u and v really corresponds to reverting space. Another remark is that this Radon-Nikodym derivative, so here I wrote it like that because I wanted to really explain the symmetry between u and v, but this product of two things simplify. We get just, it can be written as just one exponential functional to the power minus u minus v times just an exponential. And when we have a process that is reweighted by exponential of the terminal time of a process, this is well known by the Cameron-Martin theorem that this just corresponds to adding a drift to the process. So instead of saying that the Radon-Nikodym derivative is this thing, we could say that the process capital X is absolutely continuous with respect to Brownian motion with drift minus v. And the Radon-Nikodym derivative now is just this exponential functional to the power minus u minus v. And then it implies that when u plus v equals 0, we can remove this, and the Radon-Nikodym derivative will just be 1, so that X is a Brownian motion with drift minus v. So on this formulation, it's now relatively easy to see that when u plus v equals 0, the process is just a Brownian motion. The third point that I wanted to discuss is what happens when u plus v is negative. So this, of course, we cannot deduce it from the result of Corwin and Kpz because that was a restriction in their method. But one can make some conjectures because this Radon-Nikodym derivative, exponential functional to the power minus u times a slightly different exponential functional to the power minus v. This makes perfect sense when u plus v is negative, and it's also integrable. I mean, integrable with respect to the law of Brownian motion for u plus v negative. So one can perfectly consider processes X that are reweighted with respect to by these sort of functionals. And in our paper with Pierre Doussal, we conjecture that actually this description of the stationary process that I've discussed in the previous theorem, this should hold for any u and v in R, not just for u plus v positive. So more precisely, we believe that there exists a unique invariant process HUV, and that its distribution, if we look at the multi-point distribution as a function of uv, it should be analytic in uv, and the theorem should hold for any uv. We also believe that the theorem holds for any interval length L. So this is a this conjecture could certainly be proved. It's a bit more technical. It's just that in the result of Corwin and Kpz, they took L equals 1, but I believe that with some extra work, one could consider any interval length L. The first conjecture, however, is more difficult, and another conjecture is that if it's true that the result holds for any interval length L, then we can play with those parameters. We can play with the U and V, send them to infinity. We can also play with L and send it to infinity. And this is interesting because it's pretty natural to conjecture that the limits of the stationary process HUVL, as L goes to infinity, becomes invariant measures for the Kpz equation on R+. And it turns out that the L to infinity limit of those stationary process, it was have been studied. There is a paper that answers exactly that question for all U and V. This is a paper of Aria and Marchior from 2004. It was so this was totally independent from the Kpz motivation. At that moment, it wasn't known that those processes were related to the Kpz equation. Their motivation was to better understand identities related to exponential functions of the Brownian motion, in particular the Matsumoto-Yor identity. And they expressed the limits of these processes HUVL as L goes to infinity in terms of geometric Pitman transform. If you don't know what is the geometric Pitman transform, it doesn't matter too much. This is it's just some exponential functional of a Brownian motion. The definition, so in order to state the result, I will define some processes HUV. So now I don't have a superscript L anymore. These will be defined on R+. This definition is slightly different from Aria-Yor, but it's equivalent. So for any parameter U, which corresponds to the left boundary, and for any parameter V, which is less than 0 and less than U, we define a process HUV, which is the log of the sum of two things. So we have the exponential of, so we have B1 and B2, which are Brownian motions with drift minus V and V. And W is a random variable distributed as the inverse gamma distribution with parameter U minus V. So it means that 1 over W is a gamma random variable with parameter U minus V. And B1, B2, and W are independent. So it's the definition is a bit complicated, but you will see a bit later in the talk where it comes from. When U equals V, this process HUV, so one can assume that 1 over W becomes 0, and then the process HUV is just B2, so it's a Brownian motion with drift U equals V. And when U equals minus V, it can also be shown, although it's less obvious, that HUV is a Brownian motion, again with drift U equals minus V. And so the result of Aria and Yor says that you pick U and V somewhere, and you look at the law of HUVL that was defined through a weighting of the Brownian measure with this explicit Radon-Nicotin derivative. And you look at the L to infinity limit, and it will converge. So depending on where is the point UV in the three regions of the diagram. So if you are here, for instance, in the red region, then the process converges as L goes to infinity to HUV of X. And if you are here in the blue phase, then it will converge. It will not depend on V, the limit, as L goes to infinity, and it will converge to HU0 of X. And if you are in the green region, it will converge. It will not depend on V either. And it will converge to HUU of X, which actually is just a Brownian motion with drift U. So that's the result from Aria and Yor in 2004, and so these should be the stationary measures of the Kpz equation on R+. If we believe the fact that the L to infinity limit of stationary measures on 0L are indeed stationary on R+, and this can be proved. So this is a very recent result that we have obtained with Ivan Corwin. The paper is not on arXiv yet, but it should be in a few days. So we take U and V. We don't need to assume that U plus V is positive because this is proved in a way that doesn't rely on the Corwin-Kneser result. So we take any u and v with v less than 0 and u, and then one can show that the process HUV is stationary for the Kpz equation on R plus with the boundary condition u. So for every boundary parameter, we have a one parameter family of processes that are stationary for the Kpz equation on the half line. We conjecture that this family of processes constitute all the extremal stationary measures for the half space Kpz equation, and they arise as a large time limit of the Kpz equation, where the u is fixed by what is the boundary condition of the dynamics, and the parameter v will depend on what is the initial condition. So more precisely, if we take an initial data such that h0x has drift minus v at x equal infinity, by that I just mean that the limit of h0x will be minus v times x. Well, the limit of h0x divided by x will be minus v. Then the process htx minus ht0 will converge to, so this is the same phase diagram as before. It will converge to hu0, huv, hu, depending on where is the point uv in the phase space. So I think that's all for the results. And I have not so much time to explain what goes into the proofs. So the proofs are different in the case of the interval and the case of R plus. So in the case of the interval, the complete proof relies on works by many different people, and it starts from 1993. So in that case, it goes through ASAP. So the discretization of the Kpz equation that we use will be ASAP. And so the question is to find invariant measure for ASAP on a segment on a finite domain. So this has been, so a method was proposed by Derrida, Evans, Hakim, Pasquier, the matrix product on that method, and then so some concrete implementation of the matrix product on that proposed by Uchiyama, Sasimoto, Warati allowed to prove Laplace transform formulas for the to characterize the multi-point distribution of the invariant process for ASAP. So this was done by Brick and Veselovsky in 2018. And then one has to consider the limit to the Kpz equation. So show that the processes, the stationary processes exist in the limit, and also show that the Laplace transform converges to something, to some formula. This is in practice quite difficult technically, but this was done recently by Corwin and Knizel. So the Kpz equation limit. So the fact that ASAP converges to Kpz equation in a finite interval. This was done by Corwin and Shen a few years ago, and the limit of the formulas of Brick and Veselovsky were studied in a more recent paper of Corwin and Knizel. And then there is the last step, which is we have this complicated formula, but what does it mean? One has to invert the Laplace transform. So as I said, I think a bit earlier, there was a first inversion proposed by Brick, Kuznetsov, Wang, and Veselovsky. Then in a physics paper, we proposed a slightly different description, but which can be shown to be equivalent, and it has been shown to be equivalent in a paper of Brick and Kuznetsov. So I don't know exactly what I want to explain. So the matrix product on that, how to find invariant measures for ASAP. So here we consider ASAP on a finite segment. We have reservoirs on both sides with rates of injection and ejection. So these are traditionally written alpha, beta, gamma, delta. And the matrix product on that, the result of Derrida, Evans, Hakim, Pasquier, is that if we look at the characteristic function of the state of the system under the stationary measure, it can be written in a quite algebraic form. So we have two matrices E and D, and we look at the product of E plus TID, and this we sandwich it with two vectors W and V. And provided that the matrices E and D and the vectors W and V satisfy the relations that are written below, then this equation will describe the generating function of the state of the system and the stationary measure. But then one needs to, in order to do concrete computation, well, we need to find explicit matrices E and D. And so some representations were provided in the first paper of Derrida, Ivansekin-Pasquier. Others were found in later papers. The representation is not unique, and there have been several approaches. The approach that eventually leads to the stationary measure of the Kpz equation is a representation found by Uchiyama, Sasamoto, and Waradi, which uses Askey-Wilson orthogonal polynomials, and this allowed Brick and Veselovsky in 2018 to have some convenient formula for the Laplace transform of the stationary process of ASAP. It's still quite complicated. It depends on the process, on some auxiliary process AW, which I call the Askey-Wilson process. And it's a stochastic process satisfying many interesting properties. So I don't think I really want to go through these two paragraphs. So it's built using Askey-Wilson polynomials, which are very so there is a whole hierarchy of orthogonal polynomials. Askey-Wilson polynomials or sit on the top of this hierarchy, and they depend on many parameters. And these processes have nice properties that if one evaluate some orthogonal polynomial into them, then it yields some martingales, and they have many properties. But actually, I want to explain to give just a little sense of how Brick and Veselovsky suddenly arrived at something like that. And for that, I will discuss martingales and harnesses. So as I just told you, so these Askey-Wilson polynomials are related to martingales. There are martingales popping up, and all probabilists know that martingales are useful. So here on this slide, you have a depiction of a martingale on the left, and the harness on the right. So a martingale, in a sense, it controls the horse in just one direction. So the horse cannot lift his head up, and the harness is much more is more precise. The horse cannot go forward nor backward, and there are so what is a harness in probability? So a harness is a process that is sort of controlled both forward and backward. So we say that a stochastic process H is called a harness, is for every S, T, and U. If you condition on what happens before S and after U, then the expectation of HT will be the linear interpolation between HS and HU. So it's some sort of variant of the concept of martingale. And for several motivations, people were interested in quadratic harnesses. So a quadratic harness, this is when you look at the second moment of HT, again, conditionally on what happens before time S and after time U, then this is a quadratic form in HS and HU. And Brick and Veselovsky were interested in these because some quadratic harnesses appear in non-commutative probability, in free probability. And in 2010, they found that these two conditions, being a quadratic harness, typically determine HT, and solutions can be constructed using orthogonal martingale polynomials. And the Askey-Wilson polynomials, so using a pretty general family of orthogonal polynomials, provides a way to construct a large class of quadratic harnesses. And so this is how, being some specialists of this Askey-Wilson polynomial and quadratic harnesses, they at some point realized that these formulas were satisfying the conditions that relate to the stationary measure of ASAP. And then, so then after taking the limit to ASAP, Corwin and Kpz wrote formulas for the Laplace transform of the stationary process. So as I told you, the formulas are pretty complicated. So this is an integral of P0 T2, P0 S T2 T1, and these P0 are expressed in terms of gamma functions. I don't want to enter into the details of this. You don't need the details. I just want to give some vague idea of how such Laplace transform formula can be inverted. So at least the way we did it with Pierre Le Doussal. So here, when I wrote this this gamma with plus and minus, it means that we have to take the product over all choices of pluses and minuses. And this sort of expression arises very often in another context. So this is what my colleague Pierre Le Doussal calls Liouville quantum mechanics. So Liouville quantum mechanics is something that was used a long time ago, a few decades ago, in order to compute exponential functionals of Brownian motion. There have been many papers of Comte, Montus, Texier, and others in the 80s and 90s. And very recently, for another purpose, we also use that method with Pierre Le Doussal, and this is how we realized that this blue expression that arises in the stationary measure of Kpz is related to this. So the Liouville Hamiltonian is the operator Laplacian plus exponential, the exponential functions that act multiplicatively. It is well known that it's diagonalized by a family of eigenfunctions, of orthogonal eigenfunctions, which are essentially Bessel functions appropriately renormalized, so that the eigenfunction is k squared over 4, and these are orthogonal. So we know very well the spectral theory of this operator. And this eigenfunction, they satisfy many nice properties, in particular this integral identity, which involves exactly the same blue term as I showed you in the formula of Corwin and Kpz. I call this a Cauchy identity because there are generalizations of that identity. In particular, there are multivariate generalizations of this identity where typically this sort of identity is called a Cauchy identity. And so using this sort of identities, one can rewrite the formula of Corwin and Kpz entirely in terms of those eigenfunctions. And so this already provides some way of describing what is the stationary process. This is essentially what was done in the paper of Brikosnes, Wang, and Veselovsky. And one can go a bit further by using the Feynman-Katz formula. So if we look at this equation, dtu equals minus hu, where H is this Liouville Hamiltonian, using the spectral decomposition of the operator, we can write a fundamental solution as the left-hand side using the eigenfunctions. And on the other hand, by Feynman-Katz, we can write it as an expectation over a Brownian motion of some exponential functional. And so all the formulas that arise in the Laplace transform formula involving these eigenfunctions, they can be also rewritten in terms of exponential functionals of a Brownian motion like that. And okay, after massaging a little bit the formulas and working a bit, one arrives at the result that I've stated, that the stationary process is the sum of a Brownian motion W and some process X, which is absolutely continuous with respect to Brownian motion, with some explicit Radon-Nikodym derivative, as I said on the slide. On the statement of the theorem. So that's all I think for the Kpz equation on 0L. Other questions before I go to quickly to the case of R+?
No.
Okay. I will probably not have time to explain this. So the case of R+ goes through a totally different technique. I may not give all the details, but the main idea is what is explained on this slide. So we use a different discretization of the Kpz equation. Instead of using the height function of discrete interacting particle systems, we'll use a discretization of the stochastic heat equation, and that we'll see as a directed polymer partition function. So the fact that directed polymer partition function converge to Kpz equation, this has been known for a long time. This is This was essentially in physics paper for a long time, and mathematically this has been proved by Albert and Questel. And among directed polymers, there is one particular model, the log gamma polymer model, which is exactly solvable, and there is also an exactly solvable version in a half quadrant, so which will correspond eventually in the limit to Kpz equation or plus. And using a symmetry argument, a much simpler argument that what we had to go through for the case of the segment, one can explicitly describe what are the invariant processes, and then one has to take a continuous limit of the polymer to the Kpz equation. So one needs the statement in the for directed polymers in the half space. So this was proved first by Xuan Wu in 2018, and then a slightly different result was shown by Shalin Parekh in 2019, and we have slightly extended these two works in order to cover the cases that we need in a paper to appear with Ivan Corwin. So what is this half space log gamma polymer model? We need a pretty general version of the model that depends on many parameters. So we have parameters alpha 1, alpha 2, etc., and the boundary parameter alpha 0. We consider the lower half quadrant of the lattice, of the Z2 lattice, where on the boundary W, we have weights Wij on each vertex. On the boundary, the weights depend on the boundary parameter alpha 0. And at vertex ij, the weights are distributed as inverse gamma random variables with parameter alpha I plus alpha j. So we can see these alpha i's and alpha j as indexing rows and columns. And what we call the partition function of this model, z of nm for point nm, this is the sum over all upright paths, as shown in orange here, from 1, 1 to nm. And for each path, we take the product over the path of the weights that are along that path. So this is what we call the partition function. And the partition function satisfies some obvious recurrence relation. The paths that arrive at nm, they may either come from n-1m or from nm-1. So we have this recursion, and when we are on the boundary, we have some boundary relation. And it turns out that this discrete recursion is some sort of discrete analog of the stochastic field equation. Another fact is that because we have taken these W weights as inverse gamma with a specific parametrization, one can show that the law of the partition function is related to the theory of Whittaker functions, so some particular family of symmetric functions that arise in representation theory. And one particular consequence is that one can show that if you look at the law of partition function at a certain level m, so the joint distribution of z, mm, z, m plus 1m, etc., all the partition functions at a certain level, their joint distribution is invariant with respect to permutations of the parameters alpha 1 to alpha m. So this is highly non-trivial. You permute the weights, you permute the rows, and it doesn't change the distribution. It's very non-obvious, but this is true. And this is the essential fact that we use in order to compute the invariant distribution. So to have a stationary log gamma polymer model, so we fix the boundary parameter alpha 0 equal to u as before. U is our boundary parameter, and then alpha 1 and alpha 2, the parameters attached to the first and second row, we fix them to be v and minus v. And all other alpha i's, they would be just alpha, so some alpha. So here the weights on the boundary have parameter u plus alpha. The weights in the middle here, they have parameter 2 alpha. Think that alpha may be quite large. And then there are some special weights which I have depicted in different colors. So there is one very special weight, the one with a red square. The issue here is that the parameter should be alpha 1 plus alpha 2, but here alpha 1 plus alpha 2, this is v minus v, 0, and so inverse gamma of parameter 0, this is plus infinity. So it's a bit special. We have one weight which is infinity, but we will renormalize this and it will disappear. But this weight, this infinity weight, is very important. And then we have the blue dots are distributed as inverse gamma of parameter alpha plus v or alpha minus v. And so you have to imagine that along these two lines, it's a little bit the discretization of a Brownian motion with drit v and a Brownian motion with drit minus v. And we have the pink dot. The pink dot is an inverse gamma variable with parameter u minus v, exactly as the weight w that appeared in the definition of HUV. In the definition of HUV, it was depending on two Brownian motions, b1, b2, and a variable w, which had exactly that distribution. So w is the pink dot. And then how we show the stationarity. So we use the symmetry. So on the left, this is the exactly same partition function as I shown in the previous slide. And then I use the fact that I can exchange the parameters as attached to the rows. So I exchange the parameters associated with rows 1 and 2 and the ones associated to rows m and m-1, so that the special weights here, I move them to the top. But then I still have this red infinity dot, which implies that the path, they have to go through that infinity dot. And then they do something to arrive at the point nm. And the fact that we can force the path to go through this red dot here, it implies that if we look at the joint distribution of the ratios of partition function along the row m, they don't depend, they will not depend on what happens below the red dot, because this will cancel in the ratios. They will just depend on what happens on the two rows with colored vertices. And what happens here is exactly what happens here on the first two rows. So this is the same thing as the ratios along the first two rows. So the distribution of ratios along on the second row, it gives stationary processes for the discrete stochastic equation defined by the log gamma polymer. One can describe it a bit more precisely, but I don't have time to do that. And one can also check that when alpha goes to infinity and we rescale k appropriately, then these ratios, they exactly converge to the exponential of the process HUV that I had defined before. So it was defined in terms of b1, b2, and some weight w. And the weight w is really the pink dot that is here. So this is how one shows the existence of this family HUV of stationary measures for the half-line Kpz equation. So the form of the stationary measures were guessed using a L to infinity limit from the result on the segment. However, the proof uses a completely different method through log gamma polymers instead of ASAP. So the invariant measures for the Kpz equation on the segment are given by these reweightings of the Brownian measure by exponential functionals. And in a half space, so the large L limit of those processes was found by Aria and Yor. And as I have explained, so they are defined using two Brownian motions and some inverse gamma random variable. And one can show that those processes are stationary using the log gamma directed polymer model. And so there are one important problem that I have not addressed at all is the uniqueness and classification. So I have explained some conjectures about the ergodic limit theorems, but nothing has been done in that direction. And another comment I would like to conclude with is a mystery that it would be nice, instead of going through a discrete model, to understand directly why this reweighting of the Brownian measures are stationary for the Kpz equation. So it would be nice to have a direct understanding of the relation between this Liouville field theory that I have quickly explained and the Kpz equation. So why this produces stationary measures and what happens in higher dimensions. Both things have been studied in higher dimensions as well. So I would stop here and thank you for your attention.
Okay, thank you, Guillaume. Is there first any question in the participants' mind?
Well, maybe I'll ask a very simple question. Well, thanks for this talk. My question is, well, these Laplace transforms are related to large deviations. So can you prove all large deviations for your model in, let's say, in contact with reservoirs, and could you use that to get informations about, so by proving the dynamical large deviations to get information about your stationary state?
So proving large deviations at stationarity, or using results about large deviations in order to have information on the stationary state?
No,
I've not
proving
understood.
dynamical large deviations, and through these dynamical large deviations get informations for the stationary state.
So I don't think that one can prove dynamical large deviations for these processes with boundaries. So these processes with boundaries are typically very hard to study, and so far one has. So for instance, for ASAP, most information comes from the matrix product on that. So from what is, and there are a few other results, especially in the physics literature, but most of what is known is what happens at stationarity. What one could do also is to look at large deviations under the stationary measures using these new characterizations. But the Laplace transforms, the Laplace transforms that we start with. So for instance, the results of Brick-Veselovsky or from Corwin-Knizel are not related to large deviations.
Okay, because, well, there are these results by Jensen and Varden, where they proved large deviations for totally asymmetric, well, with periodic boundary conditions. So maybe one could try to extend that to ASAP. Of course, well, the lower bound was not completely proved, but okay, maybe this is a direction what should try to do something.
Yes. But although it's, I believe that it's quite complicated to go from periodic boundary condition to these open boundary conditions. Typically, these open boundary conditions are quite difficult to deal with. In particular, there is no conservation of number of particles and much less formulas available. But I'm not so familiar with the works that you are quoting, so I should have a look at this. Thank you.
Well, thanks.
Any other question? No. I have one very basic, Guillaume. In your decomposition that you got with Pierre Doussal, the first, so there is this Brownian motion W. I can't remember now, but does it depend on U and V, this one?
No.
No.
No, the dependence in U and V is only in the process X.
In X, okay. And so when U plus V is equal to 0, is the second process X which becomes a Brownian with drift, right?
Yes, so the first one, it stays a Brownian, and when U plus V equals 0, the second one becomes also a Brownian motion with drift. So that the whole thing is a Brownian motion with drift. And actually, so the first one has diffusion coefficient 1/2. And what I haven't said is that the law of X is absolutely continuous with respect to Brownian motion, also with diffusion coefficient 1/2. So that when U plus V equals 0, it's the sum of Brownian motion having diffusion coefficient 1/2, and so the whole thing has diffusion coefficient 1.
Ah, okay. And so when you take L goes to infinity in this decomposition, so at least formally, I don't know if so you never took L goes to infinity in this formula. In fact, you used another method to let in the half space, right?
So there are two ways to let L go to infinity. So you can let L go to infinity without rescaling the variable X. And then this was done by Arya and Yor. And so, no, of course, you can.
Okay, it is the work by Yor. Sorry.
Yeah,
okay.
It is the work by Arya and Yor. And actually, so Arya and Yor, they start from something like this radon-Nicodim derivative. This is their result, but it's a pretty non-trivial paper, and it's really, even to guess, it's not obvious to guess. It uses many relations between exponential functions of the Brownian motion, and it's really not obvious to guess what is the L2. To guess maybe, but to prove it, it's really not obvious.
Yeah,
to prove the L2
and my point, in fact, my point was, so can we see the condition V V less than U appearing? So I don't see why there is this these three different regimes, three in the diagram, with the condition that V should be less than U, and you have another and different limit. I don't see it in this formula. I don't know if.
When you, yes, this is so this is related to what it means to converge as L to infinity. So so this is a process on 0L which converges to a process on R plus. And so what we mean by that is that if we fix any compact 0L prime, then the restriction of the law on 0L prime will converge to the restriction on 0L prime to the law of the limit on R plus. But so this introduces some asymmetry between U and V. So because if you look on the compact U, this is the left boundary, it will always be felt, while the right boundary, it goes to infinity. So we don't feel it necessarily. We feel it only in some ranges of V. So if the right boundary is such that it will introduce a very high drift, then you will feel it. But in other cases, you will not feel it anymore.
I see. I understood. Okay, sorry. It's more clear. Thanks.
Thank you.
Any other question? No, so thank you again, Guillaume, and see you soon.
Okay, thank you, Marielle.
Bye.
Thanks.